Hello everyone, section 10.2, finding arc measures. You have some definitions that you're going to have to fill out here. Know the difference between a minor arc and a major arc. For example, in example 1, find the measure of each arc in circle C, where AB, segment AB is a diameter, so we know that this is diameter, so this is the center of the circle. We want to find the measure of arc AD. Arc AD is here. Now, I know it's this one and not this arc AD because it's two letters. So if it's named with two letters, it has to be a minor arc. So a minor arc has to be 180 degrees or less. So minor arcs are equal in measure to the central angle that intercepts them. So the measure of arc AD is equal to 65 degrees. Now, arc DAB starts at D, goes through A, so it has to go this way. It can't go this way because it goes through A and ends at B. So we already know this is 65. This is 180. So the measure of arc DAB is equal to 65 plus 180, which is equal to 245 degrees. Measure of arc BDA. BDA is a semicircle. Measure of arc BDA is equal to 180 degrees. Example 2. Find the measure of each arc again. Arc SQ is going to be 35 degrees, and if this is 90 and from PQR is 180, so this must be another 90 degrees. So 90 plus 35, measure of arc SQ, 90 plus 35, 125 degrees. RPQ, R to P to Q. So R to P, I could go left, I could go clockwise, I can go counterclockwise. If I'm going to go R to P to Q or R to P to Q, I've gone more than 360 degrees. I'm either going backwards or I'm going more than 360. So it must be going R to P to Q this way. So that's 180 plus 90. Measure of arc RPQ is equal to 180 plus 90, 270 degrees. Arc PRS. So again, if I go this way, counterclockwise, I go PR and then backwards to S, or if I go PR and then more than 360 to S, that doesn't work. So it's got to go PR and then S this way. So 180 plus 35, measure of arc PRS is equal to 180 plus 35, 215 degrees. All right, example 3. A survey asked people how many minutes they spend brushing their teeth in the morning. The circle graph shows the results. Find the indicated arc measures. So the measure of arc ABC, A, B, C, B is the center of the circle here. Arc ABC. Arc ABC, this is 120 degrees, 82 degrees. So this is equal to 202 degrees. ACB, 145 plus 13 plus 82. I'm going to pull out the calculator for this one. 145 plus 13 plus 82 gives us 202 and 40 degrees. Arc BD, again, must be the minor arc. So BD is going to be 82 plus 13, 95. 95 degrees. Measure of arc C to B to D. So C to B to D is almost 360 degrees. So 360 minus 13 is going to be the easiest way to do it. So 360, 50, 347 degrees. You have some theorems and some definitions to do below example 3. Example 4. Tell whether the red arcs are congruent. Explain why or why not. So here I have an arc here and an arc here. These are the two red arcs. Okay. Are they congruent? So they have to have the same measure, but they also have to have the same length or be from the same or congruent circles. So arcs that have the same measure and that are from the same or congruent circles are going to be congruent. So these two circles clearly are not congruent. One is inside of the other, so it has to be smaller. So these arcs are not congruent. No. The circles are not congruent. Even though the measures of the arcs are the same, the radii of the two circles are not the same. Part B. Where are the red ones? SR and PQ. Are the red ones. So this is 65 degrees. This is 50 degrees. The whole is 180. So 180 minus 50 minus 65 gives us another 65 degrees. Now this time, these are congruent because they're congruent, they're equal measures, and they're coming from the same circle. So yes, they are same measure, and from the same circle. Okay. Here, part C, this has a radius of 6. This also has a radius of 6 because that 12 is written above the center. So it's not the radius, it's the diameter. So these are 6, 6, 6. So all these radii are the same, which means that these two circles are congruent, which means that these two arcs are congruent. Actually, I'm sorry, this is the red arc here. But if this is 90, this is 90, this is 90. So the measures are the same. Yes. Same measure. And from congruent circles. Okay. Similar circles theorem. All circles are similar. Example 5. Space here. A researcher surveyed 2,000 members of a club to find their ages. The graph shows the survey results. Find the measure of each central angle in the circle graph. So if we have 25% of the circle, that's 25% of 360 degrees. So 25% of 360 degrees is equal to a 90-degree arc. Here we have 40% of the circle. So 40% of the circle, 0.4 times 360, 0.4 times 360 gives us 144 degree arc. So this is 90 degrees. This is 144 degrees. Here we're 27%. So 0.27 times 360 is 97.2. 97.2 degrees. And then we're left with 8%. So 0.08 times 360, 28.8 degrees, 28.8 degrees. And a simple check, and you don't have to do this, but a simple check is to add all of these up. That's going to be 1 degree, 9, 16, 20, 10, plus 4, plus 97.2 plus 28.8 is 360 degrees, all the way around the circle. That was example 5. Example 6. A circular swimming pool with a 16-foot diameter will be enclosed in a circular inside of a circular fence from the pool. What length of fencing material is needed? Round your answer to the next whole number. So in a situation like this, you would always round to the next. You always round up, because even if it was less than 0.5, if you round down, you're not going to have enough fence. You're going to have a hole in your fence. So common mistake is to say, well, if we've got a 16-foot diameter and we add 4 feet of fencing around it, then we're going to have a 20-foot diameter, but that is incorrect. Here is our pool with a 16-foot diameter, and here is the fence, and this is 4 feet. Feet, which means this is 4 feet and this is 4 feet, which means I've added 8 feet to the 16-foot diameter. So now circumference equals pi d. The diameter of the fence is not 20, it's 24 feet. So 24 pi, and we're going to round this to the next foot. So 24 times, use the pi button, so 75.398. If we're going to round that up, even though this would round down normally, we're rounding to the next whole number, 76 feet of fencing. Example 7 is my favorite problem of the year. This is not our first time seeing this problem. This is my favorite problem for a variety of reasons. One, Eratosthenes is finding the circumference of the Earth before they thought the world was flat. He knew it was a sphere, or the ancient Greeks believed it was a sphere. And he calculates this measurement with 2 really simple, easy to find measurements. And with those 2 numbers, he's able to calculate the entire circumference of the Earth pretty accurately, or we're about to find out how accurately he does it. So back in 3.1, 3.2, we learned about this problem. We knew back then that angle 1 and angle 2 are going to be congruent because they are alt-int angles. So Eratosthenes measures angle 2 as 7.2 degrees. Okay, he measures this actually very easily. He uses a little bit of right triangle trig that we learned in the last chapter, chapter 9. he's able to measure the length of the shadow and either measure this angle or measure this height of the vertical pole. It's probably easier to measure the height of the pole and the length of the shadow. He measures the height of the pole and the length of the shadow. He's going to use some inverse tangent, and he's going to find that that angle measure is 7.2 degrees, which means that angle 1 is 7.2 degrees. 7.2 degrees is what fraction of the circle? What we just did a few minutes ago when we were doing this problem. We were doing percent of the circle, right? We were doing fractions of the circle. So 7, and we found that 90 degrees is 25% of the circle, or 1/4 of the circle, or 144 degrees is 40% of the circle, right? Or 2/5 of the circle. So what fraction of the circle is 7.2 degrees? So 7.2 out of 360 degrees is equal to 7.2 is the fraction of the 360. The fraction of the circumference that we work with is the distance from Alexandria to Syene or modern-day Aswana. This was the hardest part of his entire calculation. How do you measure the distance between these two cities? That was really difficult for Eratosthenes back then. He certainly didn't have Google Maps to look up that distance. I've looked it up with Google Maps, and it's approximately 500 miles from Alexandria to modern-day Aswana, or what was then the city of Syene. So the 7.2 matches up with the 500. And then the denominator is the circumference of the Earth, the approximate circumference of the Earth. Assuming that the circumference, that the Earth is a sphere. It's not a perfect sphere. We know that now, but it's pretty close. It's more narrow. It's a smaller sphere at the equator than it is for the lines of longitude. But he didn't know that, and this is still pretty accurate measurement. So a little cross multiplying. This actually reduces 7.2 and 360. 360 divides evenly by 7.2. It's actually 1/50th of the circle. Equals 500 C. Okay, cross multiplying. C is equal to 25,000 miles. That's his answer to part A. Now, we don't know Eratosthenes' actual answer. We do know that he measured the angle at 7.2 degrees. The problem is the units that they used for their measurements between two cities has been lost over time. It was called a stadia. But nobody, historians, mathematicians, don't know how long that measurement is in miles or kilometers or anything. The distance of a stadia has been lost in time. So, but if we use 7.2 degrees and the 500 miles that we know to be the distance between Alexandria and Syene, then we come up with Eratosthenes' measurement for the circumference of the Earth is 25,000 miles. The actual circumference of the Earth is 24,902. He's only off by 98 miles. Now, yeah, 98 miles is not a short distance, but 98 miles compared to 25,000 miles, or 98 miles compared to 24,902 miles, if we do what fraction, 98 out of, or what percent, 98 out of 24,902 is, so 98 divided by 24,902, he is off. That's 0.0039, or less than, he is less than 0.4% off. That's incredibly accurate. That's 99.6% accuracy. It's incredibly accurate. Back in 220 BCE, so approximately 2,240 years ago, he was off by less than 1%, less than half of 1%. All right, example 8. In one revolution, how much further does a point 10 centimeters from the center of a record travel than a point 3 centimeters from the center of a record? This point's going to travel further because it's got a bigger circle to go around than this point does. So what's the circumference of the point 10 centimeters away? So C equals 2 pi r, so 20 pi for the 10 centimeter circle, and the circumference for the 3 centimeter circle is, again, 2 pi r. This is equal to 6 pi. So how much further does it travel? 20 pi minus 6 pi is 14 pi. These are centimeters, or approximately, I'm rounding to the nearest tenth, 14 times, hit the pi key, approximately to nearest tenth, so approximately 44.0 centimeters. And yes, you do want that 0.0 there because we are rounding to the nearest tenth. That was example 8. Example 9. Find the value of x. So x is here and here, making triangle AOB isosceles. This is 70-degree arc. That makes this a 70-degree angle. If this is a 70-degree angle, this is a 110-degree angle, which means that I have 70 degrees left to split between these two evenly. So 2x equals 70, x equals 35 degrees. At 11 o'clock, the hands of the clock form an angle of blank. So here's our clock. There's noon, 11, 12. There are 12 of these going around. This is 1/12 of those. Okay, 1/12 of the circle. So what is 1/12 of 360 degrees? 1/12 times 360. 360 divided by 12. This is a 30-degree angle. That's the end. Thank you very much. Bye.